Foundations of building a large language model. When we think of building a large language model, we need to know few facts. And in this sequence, in this session, we'll try to understand those building blocks or starting point. One is you need to have basic idea. Yes, you will not be doing any programming, true. You can use Playground to ask clarifications about the code or maybe to enhance the code. We should know that why we are using TensorFlow or PyTorch, encoders and decoders, selecting and collecting suitable datasets, data cleaning and preprocessing, and positional encoding. What all these terms means for this development of large language model, building of the large language model. TensorFlow and PyTorch. What is TensorFlow? It is open source from Google. It is a declarative toolkit available where you can store the words and text in terms of vectors, scalars, vectors, and tensors. Everything can be a tensor here. For example, this number 1 is actually a scalar. Vectors means more than one dimension. For example, here we have 2 dimensions, and matrix more than 2. This is a matrix, and tensor, which is a matrix of matrix. So, declarative toolkit. Backend is C, C++, my favorite. Data flow graph, nodes are functions and operators. Edges are inputs or data or tensors. And lazy execution and eager execution options into version 1.7. The key concept, at least the bare minimum requirement, is that you understand how the variables are declared or how the constants are declared. For example, constants. You can declare constants using this like tf.constants, and these are the constants you are declaring. Variables, you can declare using variables like tf.variables. And placeholders, like placeholders is a float, is a placeholder you are creating here, input equal to tf.placeholder of data type float. Then operations, like you can add matrix, you can multiply matrix. This is adding 2 matrix or 2 tensors, add, and then matrix multiplication A and B, and so on and so forth. Sessions, you can create sessions. You can create tensors, which are nothing but multi-dimensional, optionally multi-dimensional matrix in a high dimensional space, which we deal with whenever we work with large language model. We will be using tensors. And graph relationship between vectors like this, with G as default, add and matrix multiplication examples. TensorFlow code, you start with importing. Import TensorFlow as TF. Then create a TF placeholder type, for example A and B in this case. Define their input shape as tensors. So A tf.placeholder and the data type float 32 and the shape. This is another placeholder, data type, and the shape. Then matrix multiplication, this is TF mat multiplication, that is matrix operation. Then session, create a TF session that runs the session with input parameters for the placeholder A and B in this case. Session, tf.session, print session run A and B. C as operation won't run until session run lazy evaluated. And these are examples of session output you will expect from this. This is a bare minimum understanding of the TensorFlow code, the syntax and the format. You will see the code in the programming. This is another example, TensorFlow example. In use if Use TF for input data modules like insert TensorFlow as TF from TensorFlow example tutorials, and this importing this input data. Create a model. This is how we create a model. MNIST, input data, read data set, and this is in minced data, one hot equal to true. This is creating the model. We'll be using one hot in our example code for creating the model from scratch. X, Y, X, W, B, C, these are all placeholders and the variables. And then we define our model TF variable for predicted value Y, like cross entropy equal to TF dot losses sparse sort. This is soft max, and cross entropy labels Y and logits Y. Logits is the output tokens, and this is a gradient descent optimizer. I want you to search these terms and important and meaning of these terms with examples using Cohere Playground, which I recommended. Create session, train and evaluate. This is a complete simplest possible cycle. Train and evaluate the model, and then is the final output. Similarly, what is PyTorch? It's open source from Facebook in 2017. A graph is created on the fly like X torch dot random. Then this is another example. So we are creating like this. Develop and release primarily in a Python package, and tensor computations are available with PyTorch. We'll be using PyTorch, which can leverage CPU, GPU or CUDA drivers or available on your machine. Dynamic, NN, type-based autograd, and graph-based dynamic computations imperative toolkit available in PyTorch. PyTorch API key concept, variables and autograd, like from torch import variables, and we create a variable like this. Here we are again using tensor here, and required grad equal to true, and this is Y, which is backward, that is compute gradient and back propagate the value. We'll be back propagating torch tensors. These are operations like multiplication or division or addition. How do we do it? Transformer is the idea we are going to build, where we start with input. It will have multiple encoders. This is encoder stack consisting of multiple encoders in each stack. So this is one encoder. The input, after converting to embeddings, will go to the encoder part of the model transformer along with the positional encoding. So first your input is converted to embeddings, and then positional encoding that goes to transformer. So in encoder stack, each encoder contains multi-head attention layer and feed forward layer. Each decoder stack contains two multi-head attention layers and a feed forward layer. Output contains linear layer and softmax layer. The data that leaves the encoder is a deep representation of the structure and meaning of the input sequence. Sequence of step. We will try to understand these steps, what I explained in the previous slide, one step at a time, going extremely slowly, one point at a time. Like scientists discovered a new method to generate clean energy. This is our text. Sequence of step for this would be first tokenization, then embeddings, then positional encodings, then transformer, and then softmax. The encoder and decoder stack consists of several, usually 6 encoders and decoders respectively, connected sequentially. So encoder, 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 and then the output of the encoder stack is fed into the decoder stack. So the encoder stack purpose is it processes the input sequence, for example a sentence, to produce a set of context-aware embeddings, means vector representation. It captures the relationship and features of the input data because of the vector representation, as we have understood earlier also. The role of layers in the encoder stack. It composed of multiple identical layers, often 6 or maybe 12, each consisting of two primary mechanisms. One is multi-head attention and second is feed-forward neural network. We are going to implement them tomorrow. Today we'll understand the first part. Input representation. The encoder takes sequence of tokens or token embeddings, that is word representation, and positional encoding, which help the model understand the order of tokens. Now, first encoder in the stack receive its input from the embedding and positional encoding. This is encoder number 2 in the stack. So first encoder will receive input from the embedding and positional encoding. Then other encoder receive their input from the previous encoder. So this is in the middle. Let's say we are talking about encoder number n. This encoder receives input from the previous encoder, that is encoder 1 output goes as input to second encoder. Encoder passes its input into a multi-head self-attention layer, that is self-attention layer, meaning that whatever input is coming, that we are using into a multi-head attention layer where we'll try to understand the representation or the embeddings or the data. Because this self-attention output from the self-attention is passed into a feed-forward layer. This is feed-forward layer, which then sends its output upward to the next encoder, and that is encoder number 3 in the stack. Both the layers have a residual skip connection around them, followed by a layer normalization. Like you can see here, layer normalization, layer normalization. The output of the last encoder is fed into each decoder in the decoder stack. That output from the last encoder will be sent to the decoder stack. The decoder, like the encoder, the first decoder in the stack receives input from the output embeddings and positional encoding, means whatever input was sent to encoder, the same input is sent to decoder stack as well. Other decoders in the stack receive their input from the previous decoder, like this is decoder number 1. It receives input from the embedding and it also receives the input from the encoder number 6. The output of last encoder is here to change the understanding of the tokens that will have an influence because of the output from the encoder. This is called attention mechanism. Decoder passes its input into a multi-head self-attention layer, that is a multi-head self-attention layer, and the operation is slightly different way than the one used in encoder. It is only allowed to attend to earlier position in the sequence. This is done by masking future operations, meaning that we should not consider the tokens which are not generated potentially, which will be generated after this token is created. We don't want to get influenced by the future tokens in the current token. The previous token should influence the current token, the generation of current token, not the future potential tokens. The decoder has second multi-head attention layer, the encoder decoder attention layer. This is what I'm referring here, encoder decoder attention layer. The encoder decoder attention layer works like self-attention, except that it combines two sources of input. One is self-attention layer below it, as well as the output of the encoder stack. The self-attention output is passed into a feed-forward layer, which then sends its output upward to the next decoder. Each of these sublayers like self-attention, encoder-decoder attention, and feed-forward have a residual skip connection around them followed by a layer normalization. Selecting and collecting data. That was a brief discussion about the architecture of the transformer. In short, if you ask me what do you expect, Ram? Well, I simply expect a 3-line explanation of each. A transformer 1. Transformer consists of encoders and decoders. Number 2. The encoder receives input from the text converted to embeddings and positional encoding. Each encoder have multiple layers to implement certain logic. The output of encoder is sent to in the middle of the decoder stack, which also receives an input from the same input prompt. Selecting and collecting suitable data set is a critical step that directly impacts the performance and effectiveness of the model. Here's a list of key phases of process. 1. Understanding the goal. 2. Dataset selection criteria. 3. Data sources. 4. Data pre-processing. 5. Ethical considerations. 6. Iteration and validation of the dataset. So first is, whenever you think of building a model, you need to understand why are you doing it. Is it really needed? Because as they say, there's no point reinventing the wheel. If somebody has already developed a model and the model is open source, why would you build the model in first place? So you have to have very clear objective in mind. And because you need to perform a lot of steps here, this is like for data collection. Before collecting data set, it's essential to define the goal of the fine-tuning or the building of the model from scratch. This might involve determining the specific task the model should excel at, like sentiment analysis or text summarization, or maybe legal data understanding, legal understanding of Indian laws or a specific country law, or healthcare, or you decide, or agricultural requirements, or maybe domain specific question answering. You need to be very clear that why are you building the model in the first place and what kind of data you will need. What is the intended purpose of the model which you are planning to build? Target domain. Determine the context in which the LLM will be applied as different domains, because medical, legal, conventional, conversational, they require different data sets. You need to plan, decide, collect, curate, fine-tune, label. You have to prepare the data, which take months sometime. The criteria for your data set should be relevance. The data set which you will be using to train your model, to create your model, should be representative. And it should be pertinent to the task and the domain you are planning to use your model for. It should contain text that reflect the language, terminology, and structure relevant to the application use of this model. Quality. High quality data is crucial. This includes well-structured, grammatically correct, and balanced representation of different viewpoints and sentiments. Size. While larger data sets can provide more training examples, but the size should be balanced with the quality. In order to get more data, in order to get huge data, you may lose the quality, so don't compromise on the quality. Data sources. From where can we collect the data? Well, the best thing is you collect your data yourself. But then do we have third-party apps or options or ways available which can be used to collect this data? Absolutely. There are numerous publicly available data sets in repositories like Kaggle, Hugging Face datasets, academic institutions. These can be great starting point for finding relevant data, at least when you are planning to start. If you want to build a proof of concept, and we will be using the data set as I explained from Gutenberg project, which consists of more than 70,000 free ebooks. Custom data collection. This may involve scraping websites, collecting user-generated content, or utilizing APIs to gather real-time data from social media, forums, or specialized datasets or databases. Crowdsourcing. For specialized tasks or domains, crowdsourcing method can be used to gather labeled data from individuals who are knowledgeable in that area. But once the data is collected, shall we simply go ahead and use this data? No. The data should be stripped from any sensitive information, any personal information, any harmful content. We call it as pre-processing. The raw data often require cleaning, which might include removing HTML tags or correcting typos or standardizing format and filtering out irrelevant information which might be there in the data you collected. Annotation data. If the task required labeled data set for supervised learning, you need to annotate it properly. This could mean that tagging parts of the speech or annotating sentiments or classifying text into categories. Balancing. Ensuring the data set is balanced across different classes or labels to prevent biases during model training. Ethical considerations are also there when you plan to build model, when you are collecting the data, like bias awareness. It's important to ensure that the model does not inherit or amplify harmful biases present in the training data. Privacy and compliance. Data collection method must comply with legal regulations concerning data privacy like GDPR. It's essential to handle personal data with great care and seek necessary permissions before you use that data to train your model. Data for our model will be, as I said in the earlier session, Wonderful Wizard of Oz. This is from Project Gutenberg. This is a library of over 70,000 free ebooks. How it works? Let's understand. Imagine you are writing a news article about a scientific discovery. And the first sentence is, scientists discovered a new method to generate clean energy. This is the first sentence. So first step is tokenization. Scientists discovered a new method to generate clean energy. It first be tokenized. So these are individual tokens created from the text. Scientists discovered a new method to generate clean energy, full stop. This is the first step, and this is what we are going to implement today. The sentence is broken down into smaller pieces called tokens. The choice how to break down the sentence depends on the specific tokenizer used. You build your own or you use existing one. We will be building also and we will be using existing also for clarity, so that you understand even if you are using the pre-built tokenizer, you will have the clarity how this might be working. Then positional encoding. Positional encoding layer represents the position of the word in the vocabulary. Model needs to know the order of words in the sentence as well. Model adds information about the position of each word to this. Thank you so much. That's all for this session. Basic understanding. We'll proceed with the next part, which will go into the further down in the subject. Thank you so much, team.